Hello everyone, my name is Caroline and I'm going to present the work Effective Monte Carlo Simulator of Whole Transport in Silicon Germanium Alloys. In my presentation, firstly I will make an introduction of the work, then I will present the methodology used to develop the Monte Carlo Transport Simulator of Holes in Silicon Germanium Alloys. Then I will show the results and finally the conclusions. Our interest in studying the transport of holes in silicon germanium alloys comes from the idea that silicon germanium alloys could substitute silicon on p-type transistors. And this idea is supported by previous papers, which have electrically characterized silicon germanium p-type transistors and have showed that silicon germanium p-type transistors have a higher performance in comparison with silicon p-type transistors. Besides that, in the past years, some literature reports have showed that the degradation of NBTI is less significant on silicon germanium p-type transistors than in silicon p-type transistors. So we have developed an ensemble Monte Carlo simulator of hole transport in silicon germanium alloys. And this transport simulator can be easily coupled to an electrical field solver to build an atomistic device simulator, which can be used to investigate the electrical properties of silicon germanium p-type transistors and the reliability of silicon germanium p-type transistors. In the next slides, I will show the methodology used to develop this simulator. In a Monte Carlo transport simulation, the movement of holes is described as free flight periods that are ended by scattering events. During the free flight periods, the holes are only subjected to an electrical field, and at the end of the free flight period, a scattering event must occur. The scattering events may change the energy and the momentum of holes. The trajectory of holes are updated at discrete periods of times, called time step. In these representations, they are illustrated by the blue circles, and the scattering events may occur at any moment in the simulations, and in these representations, the scattering events are represented by the red symbol. To properly describe the transport of holes in silicon germanium alloys, an analytical description of the valence band is needed. In terms of the silicon germanium valence band, it is best described considering the three-band approach, which takes into account the split-off band, the head-hole band, and the light-hole band, and these two last are degenerated. A split-off band is parabolic and spherical. Because of that, the dispersion relation of the split-off band is quite simple. On the other hand, the half-hole band and the light-hole band are not parabolic and warped. Because of that, both effects must be taken into account in the dispersion relation of each of those bands. To obtain the parameters of the dispersion relation showed in the previous slide, firstly, we calculated the band structure of silicon germanium alloys using the empirical pseudo-potential method. Then, the parameters of the dispersion relations showed in the slide before were extracted from fitting the equations of the dispersion relations to the EPM data. To determine the free flight time and the scattering mechanism that must end the free flight period, the scattering rates of each mechanism must be calculated in the simulation. Regarding the transport of holes in silicon germanium alloys, the most important scattering mechanisms that must be taken into account are the ones caused by phonon and alloy disorder. In terms of phonon scattering, they can be divided as acoustic phone scattering and optical phone scattering. The acoustic phone scattering only causes interband transitions, while the optical phone scattering can cause both intraband and interband transitions, and the alloy disorder scattering can cause interband and interband transitions. In the next slides, I will show the results of our simulations. We have calculated the hole mobility at 300 Kelvin and at low electrical field for the entire range of germanium content, and we have compared our results with experimental data and with other simulation results that employed a more complex approach. The alloy disorder scattering potential was adjusted to obtain the mobility results that best agree with the experimental results and with the simulation results. Looking at the profile of the curve hole mobility as a function of the germanium content, we can notice that the hole mobility depends on the germanium content, and this suggests that the impact of each scattering mechanism depends on the germanium content. So, looking at the graph, the occupation of the valence subbands as a function of the germanium content, we can notice that the heavy hole band is always the most occupied subband. However, for higher germanium contents, we can see that the occupation is even higher. So this suggests that the interband scattering is less likely to happen for higher germanium content alloys. Looking at the alloy disorder scattering rate as a function of the hole energy, we can notice that for the silicon germanium alloy that has 0.5 germanium content, the alloy disorder scattering assumes its highest value, which means that for this alloy, the alloy disorder scattering rate is more likely to happen. On the other hand, for the silicon germanium alloy that has the highest germanium content, the alloy disorder scattering assumes its lowest value, which means that for this alloy, the alloy disorder scattering is less likely to happen. Now, observing the phonon scattering rate, which is the sum of the acoustic and optical phonon scattering rate, as a function of the hole energy, we can see that for very low energy, the silicon germanium alloy that has the highest germanium content has also the highest phonon scattering rate. However, looking at the energy of interest at 300 Kelvin and at low electrical field, the silicon germanium alloy that has the highest germanium content has the lowest phonon scattering rate. Finally, I will show the conclusions of the work. So we have showed that our mobility results agree very well with experimental and theoretical results. Besides, our model is efficient and it is less computationally expensive. We have also discussed how the hole mobility in silicon germanium alloys depends on germanium content. High germanium content alloys have lower scattering rates, and because of that, the holes present higher mobility. However, intermediate germanium content alloys and low germanium content alloys have higher scattering rates, and because of that, the holes present lower mobility.